that I have changed. I don't know that I've changed the order of these questions, and I remember that when I set it up, it was not necessarily in the best order to do them. So I might not do them in order. These are all questions that when I made it, they're from old homeworks or old tests, so they're good things to know how to do. And let's start. I think we're going to start with this one. We're going to do some together, then you're going to do one on your own, and then we're going to practice with something that's going to be very like your lab tomorrow, so that everybody will feel comfortable. You'll go into lab, you'll know just what you're doing, and it'll be great. All right. Okay, so our directions for this first one are to construct the state table for this circuit. So what you're going to be looking at, and again, I don't know why people are really resistant to this, but I've found that they are, is that the best way to program a finite state machine is to have two always blocks. You have one always block that determines what the next state is going to be, and then you have another always block that actually advances it to that next state. And so if you look at this code right here, you see that it has a clock, because finite state machines are going to rely on flip-flops, so you'll have a clock. This one has a reset. It's reset in. You don't need to really worry about that a whole lot. It just means that it's a negative reset, so it's like if you look at this bottom always block, it says if reset in equals 0. So it's set that if it equals 0, then you reset. So that's all you have to worry about. So it has a reset. It has T. T is your input. You have your outputs, U and V. And then you have this reg. You have little y and capital Y. I usually call those, what here are little y and capital Y, I usually call them next state and current state. That way I don't have to keep track of what's lowercase and what's uppercase.
Next normally uppercase?
Next is normally uppercase and current is normally lowercase. But I can't ever remember that, and I do them backwards. And then you set some parameters. This is completely optional, but it just makes it so that you don't have to remember what the binary values are for each of your states. So when you look at this, it kind of tells us we have three states. We have a state D, we have a state E, we have a state F. We might also have a reset state. I'm not sure yet. Okay, so then I take a look at this first always block, and this first always block is going to tell me what to do depending on what state I'm in. And I see that, let's see, my output is assigned elsewhere. I often do my output in this always block, but you don't have to. When I look at my output right here, assign U equals Y equals E, assign V equals Y equals D, or Y equals E. The one thing that I notice is that U does not depend on my input T. Since U does not depend on my input T, I know that this is a Moore machine, because it only depends on the state that I'm in. So I'm going to make a state table. So I'll have current state, and I'll have next state, and this is going to be if T equals 0 or T equals 1, and I'll have my outputs. I have two outputs. I have U and V, and because I determined already there was a Moore, I don't need to have separate columns for T equals 0 and T equals 1, because it doesn't depend on those. So I'll look at current state being D. So this always block says, based on my current state D, if T, this means if T equals 1, I can't read that, if T is the same as saying if T equals 1. So if T equals 1, then capital Y is our next state, then our next state is D. So if T equals 1, our next state is D. Else, our next state is F. And I'll come back and do the outputs in a minute. Then we have, if our current state is E, if T equals 1, our next state is E. Else, our next state is D. And then we have F, if our current state is F, if T equals 1, then our next state is E. Else, our next state is F. And then we have a default, and our default, that would go with anything, so I can just put default. The next state would be D. Okay, and then it tells us, that's telling us what the next state is going to be. But you don't actually go to the next state until you have a clock edge. So at the positive edge of the clock, or at a reset, at the negative edge of reset n. And so if reset n equals 0, then our next state is going to be our current state. Now we're setting our current state. Our current state is going to be D. Otherwise, you make your current state equal to what you calculated up here. And then here we're defining our outputs. It says assign U equal to Y equals E. So Y equals E, that statement right there equals 1 when the current state is E, and it equals 0 when the current state is not E. And so Y equals E has the value true if Y is E, and false if Y is not E. So U equals 1 if you're in state E, and it equals 0 if you're not in state E. And V equals 1 if you're in state D or E, and it equals 0 if you're not in state D or E. And did this say state table or state assigned table? State table. So, but it would be easy enough to do state assigned table because we already know what everything would be. D would be 0, 0, E would be 0, 1, F would be 1, 1, and then this default we would fill in with 1, 0. So are there any questions on that?
Why for the state F is this, like, for state E, you have T is 1 is E, and then for F you have another E, but it's 0, and the one above it gives you a 1?
For the outputs?
Yes, ma'am.
Okay, so the outputs don't come from the state because, the outputs do come from the state. So to get the outputs, I'm looking at these lines right here. So U, right here, it says U is going to be 1 when I'm in state E, and V is going to be 1 when I'm in state D or E, and if I'm not in any of those states, U or V will be 0. but I'm not sure that was your question.
No, I get it now. It's the current state, not the next state.
It's the
Okay,
current
now-
state, not the next state, yes. Yes. Okay, other questions? All right, let's try another one. So I want to skip 2 for now. And I want to go to 3. And for 3, it says to do a state diagram. Now, notice this one, I am defining my output within my case statement, which is how I normally do it, but I do have a different output for different inputs. So like, if you look at case A, it says if X, and then it tells us what our next state is going to be, and it tells us what our output is going to be. And so our output is depending on our input. So that tells us this is going to be a Mealy machine. And this time we're going to do a state diagram. So we have, how many states do we have? 3. And I can't write the output on the states because it's Mealy. I have different outputs for different inputs. So I'm going to look at my second always block to determine what my reset state is. So it says if reset n equals 0, then my current state is going to be A. So that's telling me this is my reset. Your second always block is usually going to be something like always at positive edge clock. Current state becomes equal to next state. That's what your second always block is almost always going to be. You might have other stuff in there, but that's going to be the main part of it.
Is that when it's doing the reset and then the current state versus next state is the Y,
Yeah, so
small y to Y?
so I usually just use current state and next state just because they mean more to me because I can't remember which is supposed to be uppercase and which is supposed to be lowercase. And so, and if you have a reset, it goes in there, but you don't always have a reset. So the second always block is going to almost always have something along the lines of always at, and it doesn't really matter if you do positive edge clock or negative edge clock. Current state, and then whatever you're calling these, current state becomes equal to next state, and it's the next state that you are defining up in the first always block. And so here, the current state is lowercase y, and the next state is uppercase y. And then your first always block is almost always going to be something along the lines of always at current state, or whatever your input is. So input var, whatever that happens to be. And then you're going to have a case statement. And then inside this case statement, you're going to have current state. You're going to say based on what your current state is, whatever your variable for that is. And then if you set up parameters for your different cases, you could use those. If you didn't set up parameters, if you just had binary numbers, so case, when you have 0, 0, or you have 0, 1, or you have 1, 1, and if you don't use up all of your binary numbers, make sure you have a default. And then under each of these cases, this is going to be where you say what the next state is, and maybe output.
So that builds like a multiplexer?
It builds more than a multiplexer. You definitely use case statements for multiplexers, but this is building a finite state machine. So this is it's putting,
The module?
yeah. So I'm not, the hardware would actually not necessarily be a multiplexer. It would be, you'd have some flip-flops and stuff, but yeah. Okay, all right, so that's what your two always blocks are going to be. So in the one we have right here, we have, this is not going to be visible on the video. Okay. So we have if we're in case A, if x equals 1, then the next state is B. So we'll draw an arrow here, and we put a 1. And it says our output, which is R. Notice output R up here is 0. One thing that's also real important is your next state and current state have to be defined as reg, because they're in an always block. And if you're defining your output in the always block, it's a reg. I actually usually do, to be on the safe side, you can do your output here. I usually do, depending on what kind of machine it is, I might do next output, like next R, and next R, depending on what kind of machine I've got. Okay, so, and then it says else begin y equals c. So if x is 0, we'll go to c, and our output will be 0. And then if I'm in state B and x is 1, I'll go to c, and my output is 0. And if x is 0, I go to A, and my output is 1. And if I'm in state C and x is 1, my next state is C, and my output is 1. And if I'm in state C and x is 0, my next state is B, and my output is 1. And I have a default, which I don't need to draw on my state diagram because I'm not using it. It's my don't cares. And that's my state diagram. And my volume is turned off. I sure hope it's recording my voice. There we go. Let's see. So any questions on this one? Wake up. No? Okay. It wouldn't be a session without that. Yes?
Y from A, when it goes to C, for 0.
Did I do it wrong? Let's see. Okay, so from A, when x is equal to 0, y, the next state is C, and the output is 0. So R is my output, and I see that up here because it's output red jar. Yes.
Just double checking, but the reason why we're using a parameter to define the state's values as opposed to just writing it down is just for clarity of code, right?
Convenience, yep, and clarity, yep.
Right.
It can be very useful when you're doing your project, whatever your project is going to be at the end, if it has like some sort of physical meaning, like when they do the elevator project and it's referring to floor 1 or floor 2 or something, so you can keep track of what it is in your head that you're trying to model. All right. So let's do number 4, and then y'all are going to do one on your own, and then we're going to write the Verilog. And I think it sounded like I just got a Zoom person. Or did I log out of Zoom? Oh. We'll see. There is someone there. Okay, Luke, can you hear me and can you see things? Yes, yes. Okay, good. All right, excellent. Okay, all right. So now I was here, and I'm not sure. Did I have instructions on number 4 of what to do with it?
Not sure.
Just not sure where I got it. Okay. All right. So we're just going to draw a state diagram just to make sure we know what's going on with it. So we see that we've got 5 states, A, B, C, D, E, and we see that our output is being defined outside of this always block, so that gives us the idea that this is probably a Moore machine. And when I look at my output, I see that Z equals Y equals C or Y equals E. That tells me that it depends only on the state, not on the input, so this is in fact a Moore machine. So I've got my 5 states, A, B, C, D, and E, and I can already tell from my output that Z, which is my output, is going to be 1 only if I'm in state C or state E. So I can write Z equals 1 on C and E, and Z equals 0 on the other states. My input is W, And this says case Y, so based on my current state, if I'm in state A and W equals 1, then my next state is D. And if W equals 0, my next state is B. If I'm in state B and W equals 1, my next state is D. And if W equals 0, my next state is C. If I'm in state C and W equals 1, my next state is D. And if I'm in state C and my next state is 1, my input is 1, my next state is... If I'm in state C and my input is 0, my next state is C. If I'm in state D and my input is 1, my next state is E. If I'm in state D and my input is 0, my next state is B. And if I'm in state E and my input is 1, my next state is E. If I'm in state E and my input is 0, then my next state is B. My reset is going to be state A. And I see that in my second always block. If reset n equals 0, y equals a. If you ever need to do that yourself when you're designing something with the basis board, you'll just define one of the switches to be your reset switch, and then you can have it be on the negative edge or the positive edge. It doesn't really matter. If you flip it back and forth, you'll get one of the edges, and you'll reset it, and that'll make it reset. So if you ever need to have a reset, that's how you do it. You just assign it to be one of the switches, and then you just have it set in there. Okay. Any other questions? All right. So it's y'all's turn to try one on your own. So we're going to go to question 5. I think we haven't done yet, and I want y'all to try this one to do a state diagram for this one, and then we're going to practice writing the Verilog, and then we're going to see about how you would write the Verilog for your lab tomorrow. So I can give y'all a few minutes now that you're experts at this. I think you all are. Let's see. Put half of it there. I'm pausing the recording. Y'all are all going to remember to tell me to start it back?
I'll make sure.
Okay.
Class.
Oh, good. When did I do that?
Right before you,
Right before I had surgery?
I think so.
No, right after I had
Right
surgery.
after.
Right after I had surgery, right, yeah.
Oh, okay.
Yeah, I was still on pain meds, yes. Yeah, which I am off now, and beginning to wonder if that was a good idea.
Oh, no.
Yeah. Good, I'm glad. So were there questions that were similar or helpful? So I know some of you are still working, but have you determined whether it was a Mealy machine or Moore machine? Mealy. And how'd you determine that?
Says it.
What's that?
Says it. It says it.
Oh, yes. Which would be like, yeah, that's a good hint. See, I guess I could have, yeah.
The output in the case statement.
The output's in the case statement. And not only in the case statement, but different for the different inputs. Because I could have it in the case statement, like if I had it, Well, no, if it's more, it really ought to be outside the case statement. It really ought to be in the other always block. Because it's supposed to be based on the current state, and this is getting it for the next state. So, yeah. All right, so you should, I think I'm recording. I am recording. Okay, so how many states were there? 3. So A, B, and C. And which one was the reset? A. And then what is coming out of A?
0, 0 to B.
0, 0 to B. And 1, 0 to C. Because if W equals 1, we go to C, output 0, W equals 0, output is 0, and we go to B. Okay, so what's coming out of B?
1, 0 to C.
1, 0 to C,
Now moving back to B. 0, 1.
and 0, 1 back to B. And from C, 1 and 1 to C, 0, 0 to B. Okay. All right. So now we're ready to do the harder part, and that is, given the state table for a Mealy type circuit with 1 input R and 2-bit output S1, S0, and state A is the reset code, write Verilog for this circuit. All right.
So number 2.
This is number 2. And I'm actually going to, no, I'll do it here. Okay, so module problem 2. So I've got 1 input R. I've got a 2-bit output capital S. I have to have a clock because I can't have this machine without a clock, so I have to have that in there. So that's my input, my output, and my clock. And then I need to go in, it's going to capitalize all the first letters, which are not supposed to be capitalized, so just ignore that. I'm not going to, I don't want to go bother and change it right now. My input is going to be R, comma, clock. And I'm going to have output reg 1:0 S, and it's 1:0 because it's 2-bit output. And then I'm going to have reg, and I have 3 states. So how many bits do I need to represent my states? I need 2 bits. So I'll have reg 1:0 current state next state, and then I'll have parameter A equals 2B00. This is arbitrary. You can define it however you want. B equals, and you don't have to define it at all if you don't want to, 0, 1, and C equals 2B 1, 1. It's, what's that?
Oh, no, I just did the same.
It's easier to define them here because I already have letters in my state table, so that helps. All right, now I'm going to have two always blocks. So this first one will be always at current state and my input, which is R. And this, sometimes you'll need a begin and end. We're not going to need it because all we're going to have is a single case statement. And our case is going to be based on our current state. And then I'll have, if my current state is A, I'll have A colon. Now, let's see, this is a Mealy machine, and so my output depends on my input, so I'm going to need to define my output within my case. I'm going to need a begin and an end with my if statements. So I'm going to have if R. Oh, if registered trademark. If R. Begin. And the reason I need the begin is because I'm doing two things here. I'm going to say next state, and I'm going to use a non-blocking assignment just to be careful here. I don't think I need one. I think I could use an equal. So my next state is going to be C, and S is going to be equal to 2B10. And then I can end that if statement. Else, don't do it, did it. Else, and I need to begin this else statement too. Next state is going to be C, and S will be equal to 0, 0. And then I can end that else, and I didn't have to have a begin and end around my A here because all I have within my A is an if and an else. If I was doing anything else here, I would have to have a begin and an end with my A. So my A only has an if and an else, so I don't need that. So now I've done with A. So now let's do the same thing for B. So for state B, if R equals 1, our next state is C. And if R equals 1, our output is 1, 0, so that's the same. So that copy and paste worked. If R equals 0, our next state is E. And if R equals 0, our output is 1, 1. And then we have state C And if r equals 1, our next state is A, and our output is 0, 0. And if r equals 0, our next state is B, and our output is 0, 1. Now, especially because we didn't use all 4 possibilities of our parameter, so like our states are 0, 0, 0, 1, and 1, 1, and we didn't use one of them, we need to be careful and put in a default. Whether it would matter or not, I don't know, but Vivedo won't like it if you don't. So we need to put in a default. And your default can be, you can really have it be whatever you want it to be because you're not expecting to use it. But you could have, I will need a begin here because I'm not going to have an if. Because I don't care what my input is here. I just need to set a next state and an output. So I'll say next state equals 2b, and I can use XX. That's for don't care. And S is 2bxx, which is a don't care. Oh wait, there's something I'm trying to remember. Yeah. I'm going to pause for just a second. But one thing I learned in just through trial and error and practice and stuff, if you use a lot of don't cares, case X works better. And I'll research that and let y'all know for sure. But if you're going to be using a lot of don't cares, case X instead of just case X. But I'll get back to y'all on that. It shouldn't matter in this current assignment. It shouldn't matter. Okay, and then we have our second always block. Okay, so our second always block will be always at positive clock edge, pos edge clock. Now we don't have a reset here, so all we have to do in this one is to say current state becomes next state. And then we can end module.
So over here we have an end and end case.
Did I not end the case? I did not end the case. Thank you. So I do need to have an end case here.
And an end.
I need an end and an end case. Yes, I need both of those things. Okay, so any questions on that? All right. Oh, before I forget, I have been working hard at getting some things ready for y'all. If you look in your SI resources, If you look down at the bottom, right above the worksheet for today, I have some compiler resources. So I have, these are the instructions, including Vivedo, are just about how to download Vivedo, and has other stuff in there. That's old. I have instructions on how to use EDA Playground, which is an online compiler where you can put your code in and test it with a test bench. So I give examples, like an example of how to use it, and then an example with a test bench so you can see how it works. And then I also have, there's a free compiler called Icarus Verilog. And Icarus Verilog, I have the Windows instructions. I don't have the Mac instructions ready yet, but it works for Windows or Mac. And so for Windows, I'm telling you to use Notepad++ to compile and download Icarus Verilog, and it tells you how to do it. And then you can compile and you can run, and you can compile your programs and see that they work before you get to the lab. And so, like, this just gives a complete example of how to do it. So, and it's quick. It's not like Vivedo. So that will be handy. All right, so let's take a look at the lab you have to do for tomorrow. So the lab you have to do for tomorrow is six. Okay, so design a Mealy-type circuit to recognize an input circuit of either 1, 1, 1 or 0, 1, 0. Specifically, the circuit is to output a 1 when the current input is the last bit of one of these sequences, otherwise the output is 0. Note that sequences can overlap. This circuit has one input besides the clock and one output. Pretty straightforward. Create a state diagram, then a state table. Choose a minimum number of flip-flops to realize all the states. Construct a state assignment. For each flip-flop, derive the next state function, that is the function for the flip-flop's output. Also derive the output equation. You may wish to write the Verilog for your design prior to lab, but this is not required. Okay, so we're going to look at the Verilog, and then we'll do the other stuff, because at this point the Verilog will be pretty straightforward now that you know how to do a finite state machine. And so I'm not going to do your exact one. Yours is to do 1, 1, 1 or 0, 1, 0. So I will do 1, 0, 1. So 1, 0, 1. So we're trying to detect 1, 0, 1. And the way I see it, this looks to me like I would have a reset state. I would have a state where I have a 1. I would have a state where I had a 1, 0. And that's it, because it's Mealy, because it's supposed to give my output on the state where I get where I recognize my sequence. So if I have my reset state, so I'm at my reset state, so I don't have anything towards my 1, 0, 1. If I get a 0, am I headed towards one of these others? Nope. So I get a 0, and my output is 0. If I get a 1, am I headed towards one of these other states? Yes? I'm going to call this one reset, I'll call this one A, I'll call this one B. So if I get a 1, I'm headed to A. I don't have my complete sequence. Okay, if I'm at state A, if I get a 0, am I going to another state? I'm going to state B because now I have a 1, 0. Do I have a 1, 0, 1 yet?
So state A wouldn't be the reset state?
I didn't make it that on mine. I just called it reset. It's because this matches the Verilog I already wrote. I think I called it reset. Let me see what I called it.
So inside it would be reset?
Yeah, I called it reset A and B. Yeah. I remember there was a way I found to increase this font size. I don't remember the way. Okay. All right. Okay, yeah, so I just called it reset instead of A, B, and C. I don't know why. Okay, so if I'm in state A and I got a 0, I'll go to state B. My output is still 0. If I'm in state A and I get a 1, what do I do?
Loop back.
I loop back. And what's my output?
0.
0. If I'm in state B and I get a 1, where am I going to go?
Oh.
I'm trying to detect a 1, 0, 1.
You're 1? I mean, you're good at A.
I'll go to A, because if I look at what I've got, my last bits, I don't have a 1, 0, but I do have a 1. So if I get a 1, I'll go back to A and my output will be 1. If I'm in state B and I get a 0, where do I go?
Reset.
Back to reset. Does that make sense? Okay. So in my code, I did not use a reset switch, but you'll see this will look very familiar to what we were just talking about. I know there's a way to make this bigger. But I will have to find it later. Y'all can read that here. I just don't know if people can read it online. Text editor. No. Okay, well,
If you select the text, can you go back to view? Oh. It didn't. I thought it would.
no, I found it somewhere. No. Okay, well, I'll deal with it for next time. Okay, so if you look at this code here, notice I have my inputs are my clock, and I have another input, and I've got my output. So that's it. And then, just like in the one we did, I am going to change this now to, I'm not going to have this next output. So you have your output reg Z, you have your reg current state and next state, and then let's see if this makes sense. So I have this initialization here where I set my current state to be 0, 0, my reset state. You don't have to put that in there, but I put that in there just to initialize it. So I have my current state to be 0, 0, and my output to be 0. And then I have always at W. and then I have my case, current state, and then my first state was reset, and if my input was 1, I was supposed to go to my next state, and my output was supposed to be 0. And then if my input was 0, then my next state I stayed where I was, and my output was 0. And then this is going through and just doing exactly like what we did in the little exercises we did before. And the only time we got an output of 1 was when we were at state B and our output was 1. So you will have to adjust this for yours. And then I have my always block, my second always block, that all it has in it is my current state becomes my next state. So does that look familiar? And I do have my default. I should have my default. I do have my default. I should, in this default, I should assign something to z. So I'll say z equals 0. Okay, and we're going to see if this works. Let me look at the constraints. So what I like to use for my clock, and this you'll have to ask for it in the lab. There's this little external module that the button on it is debounced, and that means that if you try to use one of these buttons, a lot of times it double clicks, but this one doesn't. And I like to use this for the clock, so it's an external module, and if you plug it in on the top right, on the top row, it's the bottom right button right there, and it's pin J1. And if you can get this off the handout that has learning to program with the Basis 3 board. And so I like this. You don't have to use this for the clock. You can use a regular switch for the clock if you want to, or you can use one of these buttons for the clock. And then you just have to set a switch to be your input, and you set an LED to be your output, and that's all you need. And so I'm going to set this, well, I already compiled it with as a Moore machine, so you can come see that it works, if you would like to see that it works. And then we'll talk about getting the next state equations for your pre-lab. Let's see, what did I set it to detect? 101? Yeah, it works. Does anybody want to come see? Because I find out that I do something in the session before lab, and then the next day everybody says nobody finished the lab, and I just want to prove that it can work. So I set it to be this switch, and this is the button for the clock, and so I have 1. And I press it, and there's nothing, and 0, and I press it, and there's nothing, and 1, and I press it, and there's nothing, and there was a minute ago. And there we go. It was because I...
Wait, so you just keep moving that switch and it holds the value?
Okay, so right now it's at 1. So I press the button, and it's going to move to... Well, I don't know what state it was in. Let's make sure that we're in a state where we're, so we're in 0. Okay, so now I press it, I move it to 1, and I press it, and it should be in state A. And now it should be in state B. And now it should be in state C. Or state, back to, just find the output.
We did it as a Moore machine.
I did mine as the coding here is Mealy. This is Moore.
So if you press it one more time, then the light should go on?
Should go on. It did go on.
Oh, okay.
Yeah. It actually works, seems to me to work. I pressed it one more time, it went off. It doesn't seem to matter. To me, it doesn't seem to matter where I put it seems to just work. Like whether I put it in the case statement or in the next always block, it just seems to work. I don't know. So it's just like, so that's 0, 1, 0, 1. So it shouldn't work. It should be a more machine. It should do it on the next thing, but it doesn't. It works.
Question.
Yeah.
Just about the pre-lab. Does he want us to do like a sequential circuit that can recognize both of these?
No, you just pick one. Okay, so now let's go to the rest of your pre-lab. And we did a state diagram. Now let's do a state table.
Is it possible to write it for both without a lot of difficulty?
Yes. Yeah?
I mean, it's not difficult.
No?
I
No.
think I would send it.
Did we do a, we didn't do a table, did we? We just did a diagram. Okay. Okay, so I called mine reset A and B. And then our next state on whatever I called my input variable, W, I don't know what I called it, and then my output, and we were supposed to do mealy, right? Yeah, so W equals 0 or W equals 1. And for reset, my next state, if it was 0, and remember I was doing 1, 0, 1, and so if you want to do 0, 1, 0, you'll have to change this a little bit. Hello? Yes. Okay, so when we were in the reset state, if we got a 0, we went to state A. If we got a 0, we stayed in reset. And if we got a 1, we went to state A, and no matter what, our output was 0. If we were in state A and we got a 0, we went to state B. If we got a 1, we stayed in state A, and our output was 0. And if we were in state B and we got a 0, we went to reset. And if we got a 1, we went to A. And if our output, if we got a 0, our output was 0. And if we got a 1, our output was 1. And then we're going to have, when we do this as a state assigned table, we're going to have another row. We're going to have 0, 0, 0, 1, 1, 0, and 1, 1. And we'll have next state, W equals 0, W equals 1, output, W equals 0, W equals 1. So this would be 0, 0 is corresponding to our reset. A is 0, 1. B is 1, 0. Our output, those were already numbers, so we can just leave those. And for our fourth state, we have don't cares. So how many flip-flops do you need? You need 2 flip-flops. So this is our current state. I'll call it little y1, little y0. Did I get the capitals right? And next state is capital Y1, capital Y0. So to figure out my Boolean expression for capital Y1, so capital Y1 depends on little y1, little y0, and w. And 1, 1 is don't cares. So I'm looking at y, capital Y1. So that's this first column right here. And the first of those yellow columns is when w equals 0. So when w equals 0 and y1, little y0 is 0, 0, that's right here. That gives me a 0. When it's 0, 1, I get a 1. Oh, this should have been 1, 1, and this should have been 1, 0. Because I don't know how to make a K-map. And 1, 0 is 0. And then if I look at my second column, those are all zeros. And then to get capital Y0, we know that, again, the 1, 1s are don't cares. And I'm doing the second column. So when W is 0, they're all zeros. And when W is 1, they're all 1s. And then my output I have don't cares on 1, 1, and I have a 1 when W is 1 and Y1, Y0 is 1, 0. Everything else is zeros. So what would my Boolean expression be for Y0?
W.
Yep. So Y0 equals W. What would my Boolean expression be for Y1?
Y0 W bar. Or bar.
Y0 W bar. And for W? And if I did that right, you should end up with something pretty similar if you're doing 0, 1, 0. I mean, it ought to be symmetric in some sort of way. You shouldn't be surprised to see something that comes up very similar. So let's see what all it says to do in the lab. So minimum number of flip-flops, state design table, next state function, derive the output equation, and write the Verilog. Yeah, so. Yeah. So at the start of the lab, you're supposed to show your circuit design work. So you're supposed to show this sort of stuff. Notice that we don't really use this whole lot in the Verilog. This is like if we were designing it from scratch from the flip-flops, but we're not, really do that. But that is part of your pre-lab.
So mainly from that, the state design table.
Mm-hmm. And there you have it. So any questions? Yeah.
What is number 2 asking us to do exactly?
Number 2, choose a minimum. Okay, so this is doing the purple table right here. Yeah. that we chose 2 flip-flops and we gave them the 0, Y0, Y1. So, any other questions?
And this is more open to the last lab, but
Yeah.
my partner and I were not able to do the deplexer. We are the multiplexer, not the deplexer. And so he was wondering if he would have to have the truth table of the deplexer for the lab report.
Decoder.
Yeah,
Decoder.
decoder. No, I'm sorry, not the deplexer. But
It has been, to me, that was like a year ago. I don't remember. Let's see, let me pull it up.
and more than anything, we're wondering, like, do we need to create our own truth table? Do we need, like, can we use someone else's because we weren't able to complete the assignment?
I mean, you can also.
Oh, I see.
Oh, well, yeah, just write it on pencil and paper.
No, you can always make up the lab. You can make up any lab, and he has makeup days for making up the lab.
I don't want to rely on them.
Go to cheat sheet.
But let's see. So this is lab assignments. But yeah, but you can do the lab report without having finished the lab. You get partial credit. So I think, is that your question?
Yeah.
Okay.
It's just I can't remember exactly what the question was.
Let's see.
What it is, but we want
Design a circuit to implement S using 3D. Is this the right? Okay, create Verilog code. So what you can do with this, I mean, if you want to get, you won't get full credit, but you would get almost full credit. You could still design it and do it and test it, with a test bench and have everything work. So yes, you would need. Did I ever end up doing this? What lab is this? Lab 5?
Yeah,
this room. There's something about it that just makes me tired.
Yeah, it doesn't
I need
matter.
to like
Let's
make
use it.
caffeine in here.
Yeah. You just have to do
he's
this.
Lenting, so he can't have any
There are ways that you
So he's feeding.
Oh, that would be a good thing for me to do for Lent.
Yeah, at first it was coffee, then it was like caffeine, so I drink monsters.
No, it just,
It's
yeah. It just is like
Oh,
there's
yeah,
some combination.
crazy headaches.
Right.
I wouldn't be able to do it out.
Unfortunately, my withdrawals are only energy related.
I don't drink caffeine. You still recording?
I am. Let me stop it.